Hello, everybody. So we're into module 4. 8-week classes go quick. After this module, we'll be halfway through. So things moving right along rather quickly. We do have a lot of content to cover. So one of the things tonight is another math night, sort of introducing the topics. But this is one you've probably seen before because it usually shows up early. It's something that fits human intuition better than the regular math class stuff. So we'll kind of just cover it briefly. So another math night, a couple more questions for the math quiz whenever we have enough questions to fill that out entirely. Still one more section before we do that. And it's going to be just a quick coverage, very brief. Then we'll get into a unity example and probably still be a fairly short evening. I've almost got the grading caught up, and I did want to make a comment about that. So it does take a long time to get the grading done. We have different versions of Unity, and that's a big deal on a game engine, right? Somebody that has Microsoft Word 2016, somebody else has Microsoft Word 2020. It's no problem at all to write a Word document and open it on the other one's system. It's very interchangeable, but that's not the case with game engines. Version control is a big deal in Unity. I mentioned it the other day when Unity asked me if I wanted to update the system. It's like, you usually don't want to update your version of a game engine unless you don't have any projects going on, because we can have multiple versions of an engine installed. So we want to do multiple installations, but if our current project depends on a feature that was updated, then our current project's going to stop working. So there's a big deal with version control that we're going to talk about in more detail later. So whenever I go to grade the projects, I have to go through all the version control stuff, and that takes about 15 or 20 minutes on every assignment. So the grading for this class goes slowly, right? Even there's only that's actually where the restriction on the number of students came from. It got expanded once because when it started small, because the version control stretches the grading out so long. Right. I set up the processes, wait for the computer to reconfigure things, and then I can set up some more processes, wait for the computer to reconfigure things, and it's about 15 or 20 minutes just wait, mostly doing some small configurations and then waiting for the computer to make those adjustments so that I can open your homework and grade it, which means it takes a very long time, because then I do read every line of code you write and look through all the stuff you did. I take time with it because I want you to do well, so it's not just knocking points off. If there's an issue that even if it's not going to affect your score, I still want to make sure you know about that issue so that it doesn't escalate into something bigger in the future. So sometimes you'll have a perfect score and get like a short essay from me about something that might need adjusted, even though it didn't affect your grade, because I want to make sure everybody understands this well. But that makes the grading take a long time. I have 2 left to grade, and since it's going to take a long time, whenever I have classes like this where the grading takes a long time, I switch the order I grade in. Right? So that those of you at the end of the alphabet, in that case, you would always be waiting the longest for your grade. Right? If we start at the beginning and just go through. So the module 2 homework, is that what I'm almost finished? I'm almost finished with module 2. Then I did leave more scheduled time for grading over the weekend for module 3 stuff. So hopefully you won't have to wait as long to get some feedback on that. But I didn't just start at the beginning of the roster and go down. I did like first somebody from the beginning, then the last person in the roster, and then the beginning, and so I went back and forth this time. And when I grade this weekend, I'll probably go backwards through the roster. Or I might start in the middle and work outward, because the people in the middle of the whose name falls and puts them in the middle of the alphabet are kind of the ones that have to wait the longest for their grade this time. So I want to switch that up so it's that way it's different. Some people get, wherever your name falls alphabetically in the roster, doesn't necessarily indicate how long you have to wait for your grade to find out how you did on the homework assignments. So I'll be switching that up in different orders. So I think I have 2 left from module 2, and that's the 2 people in the very middle of the alphabet to grade.
I have a question kind of about that.
Yes.
Is there any way to like compile those and post those so where we all can kind of interact and see what the other person did on some of these assignments? I feel like that's kind of what's missing in this class, is kind of seeing the people's codes and how they came about the same solution. And
a GitHub repository would work really well. So if you want to put it on GitHub, and we could do a build, but the builds, we wouldn't be able to see each other's code. So we could probably put it on GitHub and set up some like GitHub repositories and then just share the links. Would that work, Jacob?
Maybe. I mean, I'm not saying necessarily try anything in this class right now, but maybe in the future.
That was something I did in the 148 class. I left an open discussion board to share your work with your classmates. So I can set that up, and if you want to share your code and stuff, the Unity projects are kind of big, right?
Right.
So
we can always just zip it too.
What's that?
So we can just always zip it and then share it with each other.
Yeah. That gets into version control. So why don't we do that tonight instead of the control movement? I'm going to knock that off the list and put on version control, and I'll show y'all how to, I'll show you the automated version of doing it. So you should be able to run each other's code. It seems like there's about 3 different versions of Unity going on here. And all those mini files in the background, those do make a difference. So you'll want to have the entire project, and we'll do version control after we talk about the math stuff. And then we can just zip the files and share them with each other. That sound good, Jacob?
Yeah, that, because I mean that even yesterday when people were sharing screens, I'm like, oh, that looks a little different, or hey, why'd you do it that way? I mean, just kind of little tips and tricks of what other people have learned as far as code or design, or just to kind of get contact things, just in general.
Yeah, so that sounds like a great thing. That's something I want to do in the 148 class, is share the work like that, or if you're really proud of something, show it off. Be like, yeah, I was so happy when I got this working. So I'll set up a discussion board where y'all can share the files like that. And we talked about Canvas Studio, so you can put Canvas, you can embed Canvas Studio into the discussion board directly. So discussion boards. Where's my new button? There it is. New discussion. Share projects. Upload your Unity projects. Written descriptions. Screenshots or videos with your classmates. Here. Oh, what's in the chat room? Okay, yeah, in the chat room, it's commented that there's quite a few websites where you can do this. Coding challenge types of websites that approach it like a game. Those are a great way to learn. You approach coding challenges like a game, and then it encourages people to improve their coding skills. Yeah, don't need that check box. I'll click allow liking, might as well. Not graded. And this will be available until the end of the semester. Save and publish. Okay, so yeah, so here's a spot on the discussion boards where y'all can share your work with each other. And if you want to do like a short video, obviously do a write-up. For a Unity project, it's definitely going to attach the file, so just zip it into a file. And if you do a short video like the Canvas Studio under plugins, you'll see, well, of you all, there will be a big list, but after you embed a Canvas Studio thing in a discussion board once, it goes to a short list, and you'll be able to see all of the screencast recordings you have right there. The media tabs are for comments, but so in a discussion board, you can probably turn that off and then just hit the embed button. Oop, Zoom's in the way. I have to wait for Zoom buttons to go away now. Then just hit the embed button to get that video directly in the discussion board. Attach your files. You all know how to use a discussion board. I guess the only new thing there is making sure you're aware that you can put screen capture right in the discussion board. I'll delete that. So that's there under discussions, a place to share your projects and discuss it, and maybe post if you hit a problem, post share your questions with each other, because that's also one of the best ways to learn is explaining it to somebody else, right? You might have got yours to work, but when you go to explain it, there'll be some other little subtleties. Like that's the very reason it's a tradition at colleges around the world for to have student tutors. You might understand it really well, but when you explain it, it takes it to a whole nother level of understanding. So yeah, an open discussion board for y'all to share and comment and all of those things. It will require version control, so I'm going to scribble out controlled movement. We'll do that on Monday. We've already did that on last week's assignment. The book had that. So that's not necessarily anything new. And we'll look at the version control. But the other topic this week is sort of a math thing. So we'll kind of get started or go over this quickly. Just a brief introduction to probability. Does anybody have any questions before we get into this? Okay, a comment in the chat room that's definitely worth looking at. Again, with those the coding challenge things, because approaching coding like a game forces us to improve our skills. So that's a great way to approach it. And I think it's already shown up in discussion boards and stuff in here. Everybody in this class is a gamer too. So that's it. That already fits with y'all's personalities. So I assume there's no questions as we get into this. So hopefully just from hearing that word before, you understand that that's a very important thing in our games. So the definition on probability is the mathematics of modeling random phenomena. So random occurrences, or seemingly random. We have two types of random. I didn't put them in these notes. There's epistemic random and adverb form, allelial random. Allelial random is the true random. That's like radioactive decay. The best our laws of physics can do is give a probability of an atom decaying. As far as when a particular atom is going to decay, we can't do better than the probability. For, like, say, a given sample of uranium, we know for certain that over a specific time interval, so many atoms are going to decay. We base our clocks off that, but we can't say anything about each individual atom. That is random as far as we're concerned, and it changes, right? Uranium decays with a half-life, so if we cut our sample in half, then those probabilities of when each atom will decay change. So it's truly random for what we know. The other type, and the stuff we deal with when most of our stuff is epistemic random, and that's random from a lack of knowledge. So like playing cards, a game of cards, right? When you shuffle a deck, it's very deterministic the order those cards are going to show up in, the sequence after we shuffle a deck. But well, we would say it's only technically a finite number of sequences that a deck of cards can go into. 52 cards, so we have 52 factorial ways of putting those cards together, and that's more than the number of atoms in our solar system. So there's lots and lots of ways to do it. So for all intents and purposes, that's random, even though it's completely deterministic. Or a simpler example of flipping a coin. Right? We flip a coin and it's either heads or tails. By the laws of physics, that's entirely deterministic. We know all of the forces on that coin, how hard it was spun, the angle with which it was spun at. I shouldn't say spun, because we can also spin coins. Do I have a coin on me? Or not? We can flip coins, and it's just a circle running through. But if we look at a coin on the side, coins are beveled. So if we spin a coin instead of flipping it, it's not a 50-50 chance between heads and tails. So I should be very careful with my word choice there. But either one is a completely deterministic event. So even when we spin a coin and we calculate that bevel, that's really just another thing that would have to go into that calculation with the laws of physics on air resistance and gravity and the force with which it was moved, and all of those things could be calculated, but not reasonably, and certainly not in an amount of time that we could predict the coin flip once we knew all of them, right? Because we don't know that force until the coin actually gets hit to start flipping. So we only have a split second to do that once we have all the numbers. So we would never be able to do that calculation. So the randomness of a coin flip comes from a lack of knowledge, not from actually being random. That's the kind of randomness we're talking about here, because obviously that's also applicable to computers. We can only do epistemic stuff because a machine can only follow a pattern, which means it's very deterministic, but we can make those patterns so complicated that that it's random enough for our purposes. Pseudo-random is the term programmers usually go with. It's enough that it gives the illusion of being random. So that's what we're talking about here, modeling these random phenomena. I'll also define random. I decided to put a specific definition to this, since it does apply so heavily to game development. similar causes lead to this similar events. Sounds strange, doesn't it? At least that's what I thought the first time I heard the actual definition of random. Because random is a word we learn when we're first learning to talk. So when you actually hear the actual definition of it, it almost seems strange because it's a word we've been using almost since before we could even think about things like different definitions. But similar causes lead to dissimilar events. And those last two examples, or three examples, the radioactive decay, the chunky uranium sits there and atoms in it randomly decay. Or shuffling a deck of cards. We go through the same hand motions. We might open a brand new deck of cards that's in the same order because they came off a machine that prints them out in the same order, and the packaging, I'll put them together in the same order. We open it up very first time in a brand new deck of cards, go through the same hand movements we always do, and it's in a different order than the last time. The similar cause of exact same thing for shuffling a brand new deck of cards, same order from the factory, same hand movements on our part, but it's a different order. Or flipping a coin. Right? We could try to do the exact same flip and get the opposite result. So similar causes lead to dissimilar events. And there's a little note here, I'll put by a plus sign. Unpredictability to a substantial degree is what we actually mean with it. So not too long ago, it's a big one on the news today. There's another campaign about not texting while driving. Obviously a bad idea. But because that increases the likelihood of a wreck, the chance of having a wreck. And that part we wouldn't call random, right? The texting while driving leading to a wreck would not be called, is not something we would consider random. But the details of the event would be random, right? Like, we're pretty sure there's a good chance that if you're texting while driving, you could lead to a car accident. But that's predictable. So the unpredictable part is what we mean when we talk about randomness. So like what type of car wreck? Hit a telephone pole, drive into the ditch, miss a stoplight and pull into an intersection, avoid another car that ran through a red light. That the unpredictable part is what we're referring to here. So just a couple terms. So now into probability. So first, the notation I'm going to use this evening for this evening, the evening's notes. Function notation from math class, which I believe one of the prerequisites for this class was far enough in math to see functions, and we're working on machines, so that mathematical requirement that there's a unique output for any input is definitely a requirement for machines. So looking at functions, I'll use the function notation as we're talking about this evening. So we would read this as the probability of event A happening or occurring, or whatever finishes that sentence out. So the probability of event A. And probability itself. So our basic form of probability is the number of times A does occur. So the number of times A occurs out of the total number of repetitions. And by repetitions, referring to similar causes. The total number of times a similar thing happens. The number of times we flip a coin, roll a dice, shuffle a deck of cards, watch atoms in a chunk of uranium decay. The total repetitions of those similar causes, out of those, how many of the dissimilar events were the ones we labeled as A? That's our basic idea of probability. There are a couple of key points to look at about probabilities in general. Some important things to remember. If the probability of A is equal to 0, that means absolutely no chance it will happen. I need a bigger piece of stone. Absolutely no chance. And likewise, if the probability of A is equal to 1, which probabilities of fractions, which we would lead to floating point numbers, which means they're kind of a mouthful to say, whether we rattle them off as a fraction or as 0 point blah, blah, blah. It's kind of a mouthful, so we have a way to make that easier to say in a sentence. We move our decimal 2 spots over, or we move, this is a computer class, I shouldn't say decimal. We move our floating point 2 spots over. The mantissa, if anybody remembers that word, but even the people that learn that actual word never use it. We move our floating point 2 spots over and then add in this symbol because it rolls off the tongue a whole lot easier. So 1 is 100%, and that is absolute certainty. Absolute certainty it will happen. Oops. And by it, I mean whatever we assign the label A to. So anything else has to fall somewhere between no chance and absolute certainty. So that's another thing about probability. So probability of any event is between 0 and 1. I have this nice little quote here that one of my professors in graduate level probability class started off the semester with that I really like, and that's probability is not a statement about reality. It is a statement about your belief in reality. He started off the semester with that, and I really like that quote because statements about reality are facts. But when we're talking about probability, we're not talking about facts. We're talking about chances. We're talking about uncertainty, things like that, and not facts. So it's not statements about reality. It's statements about our belief in reality. Common example is rolling dice. So let's take a 6-sided die. We'll calculate those and there's a couple examples in my notes here that use that particular one because it's so common and familiar to most Americans. But we're going to treat it in a perfect situation. We're going to treat it as like perfect dice, so that any one of those numbers written on that die has equal chances of coming up. But is that really what is going on if we were to sit down and totally do the deterministic physics on the roll of a die? Is that a fact that they're equal, or is that something we believe them to be equal? Almost like our randomness. It's equal enough for our purposes, right? Because we do not live in a perfect world. So we try to get as accurate as we can. But I just really like that quote when he said that, so I always keep that in mind, and I thought I'd share it with you all, because it will definitely apply to video games, right? Because we're defining a new reality for the game. A lot of games are based off the physics of our universe, but they don't have to be. You have to be a pretty creative person to create an entirely new set of laws of physics. But that humans are a very creative and imaginative species. So there's some out there that you could look at for inspiration and what is necessary in order to do that. Okay, is it okay if I erase these definitions? Hopefully everybody taking notes, got those down, or take a screenshot. Nobody's stopping me from erasing it. Yeah, I remember it caught me by surprise when I saw the actual definition of random, because we learned that word when we're young and just never bothered. So it's one of those things we never really bothered to check out the technical meaning of. We know how to use it. So the first note I'm going to put here is, so some things to keep in mind as we're working with probabilities, because obviously they're going to play in very heavily into game development. Where did I say this? Oh, I put that on given. So I have a quote I wanted to jump ahead and say, but I put it at a much better spot than right here. So I'll wait till there to make that the comment that was trying to flow off my tongue. But obviously, hopefully you all already realize that probability is very important in game development. And not just for games of chance, like simulating a board game where we need to accurately simulate the roll of a die, or a card game, or it's going to show up a lot in our games. Just the chance or the randomness to keep it from being the exact same thing over and over and over again. Like Pong. That's an important one for game development, is if you sit down and really analyze stuff, there hasn't really been invention since Pong. Hardware's improved. There have been refinements and expansions, but the graphics on the screen, on a two-dimensional screen, human control of graphics on a two-dimensional screen, and collisions or intersections of those graphics was the big invention for Pong, or the original one back in 1958, where it was on an oscilloscope before you even put it on a screen. I think he did call it tabletop tennis, but that was the invention. And since then, we've had refinement and expansion, and hardware has come tremendous ways, but how we put games together are still based very much off that, of the invention of the tabletop tennis. And I think it was 1958 on an oscilloscope, one of our first video games. But that's a little sidetrack. So probability, we need that random chance. We don't want it to happen the exact same way every time. We want some variety in there. And then some of our things are just games of chance. And then those are all about probability. Probably don't even have to make a note about how probability affects those. So the probability which I'm going to start abbreviating for where it's on the board because it's a long one. Probability of all possibilities will add up to 1. So kind of like this, an expansion on this right here. The probability of all possible possibilities add up to 1. Or another way to put that in English is something will happen. If we take all of the chances, all those different things that could happen, combine all the probabilities, we should get a 1 because something will happen. Mathematically, that would look something like this. Everybody seen this symbol before? The Greek letter sigma. I guess I could draw it a little neater since I'm actually talking about the symbol. The Greek letter sigma, we usually use that for a sum if we're going to add a bunch of things together. So the sum of the probability of all of our events will add up to 1. Which this immediately implies something else. So jumping into some math notation, if you haven't seen this before, the double arrow, the arrow with double lines, that means implies. So whenever we have one thing in math that leads immediately into something else, that's the symbol to notate that. So this fact right here, which in plain English is just something will happen, that implies that 1 minus the probability of some particular event will give us the probability of the complement of that event. For about 3 years now, one of the classes that y'all all would have been required to take, that intro to logic course, has used this notation for complement. So I'm going to go with that. Complement means the rest of everything else. Most of the time in a game, we're thinking one or the other, right? Like there's 2 choices we could take, and we're randomly going to pick between them to keep the things dynamic and interesting, and the storyline varying, so it's not the exact same thing every time. And, for example, our NPCs in a village, sometimes when the level starts, they're gonna we have them at a starting point, and sometimes they're gonna start walking to the right, and sometimes start walking to the left or forward, or sometimes they might turn around and walk the other direction, walk backwards from their starting point. So some sort of randomness. But if we say right or left, usually we're thinking of one or the other situation at any given time. So if we know one of them, we can immediately find the other one because of this right here, because the 2 together should add up to 100%. Or the simplest case is flipping a coin, right? We have 50-50 when we flip a coin, 50% chance. So 1 minus 50% leaves us 50%. Should be fairly straightforward. Up next is some other terms. It's okay if I erase this side over here. I'm gonna go back and forth. It's a whole bunch of stuff to write on the board, some notation and things. So things that would go into the side note, or when you go look them up. The reason I wanted to use the standard notations is sometimes when you're putting things together, you might be confused on what to do and go look for tips on Google and stuff. And if it's a probability instance, you're probably going to end up somewhere that uses the standard mathematical notation. So a big part of this is just seeing those notations so that when you go look something up, you can make sense of it. And it's almost always probabilities are functions. By their very nature, probabilities are going to be functions. Our input is that thing that was written earlier, for randomness, the similar events is our input, and one single dissimilar output is the result of a function. So probabilities, by their very nature, come in function format. Next thing, two events are mutually exclusive, which this will relate to that a lot. When you go look things up, you'll see the proper math notation and math terms. So you'll see mutually exclusive. That means they do not affect each other. Do not affect. Actually, I can do both. They do not affect or effect each other. That fits in the words here. Rolling two dice. Oh, wait, that's probably a bad example because those are going to bump into each other. Flip a coin and then roll a six-sided die. The outcome of the coin flip has no impact whatsoever on the number the die turns up. They do not affect each other. They're completely separate. In a Venn diagram, that would look something like this. Our two circles are quite a distance away from each other, so there's no overlap or anything in the Venn diagram. However you want to talk about it, the affected by or effects the other, both fit in the description of that. Or in mathematical notation, you might see it written directly. There is no intersection here, right? There's no and situation. So the probability of event A intersecting the probability of event B. So the intersection between both of them is the empty set. That's nothing or null. The empty set, the empty collection. Going back to the SDEV 120 class, I know everybody would have at least seen the set, some of the set notation there. Intersection is an and situation. And we can see from our Venn diagram here, there is no and here. They're completely separate things. They don't have anything in common. So that's mutually exclusive. The chance of one or the other is their sum. So whenever we have a situation like that, the probability of A union with the probability of event B is the sum of the probabilities. Sorry, I wrote too many B's there. Let me clean this up. I got carried away with the notation. So the probability of A intersecting B, so A and B having things in common, our and situation, is emptiness. Whereas the probability of the union of A union with B, which is our or situation, is going to be their sum. That'll be the probability of event A happening plus the probability of event B happening. Hopefully all that notation makes sense, looks somewhat familiar. union and intersection. So union, we just join stuff together. That's an or situation. And intersection, that's what they have in common. But everybody in here is a programmer. You all know the difference between and or. That's our intersection and union. It's okay if I erase this side, because not all events are mutually exclusive, and we might have to do some other stuff. We might need to take some other things into consideration. When not mutually exclusive, I'm going to abbreviate that because that's really long words. And that's going to take up the board space really quickly. When our events are not mutually exclusive, then subtract overlap. Which notationally is just an extension of this. So the probability of event A or event B, oh, again, that's our sum, the probability of A or the probability of B, minus the overlap, which would be the intersection. The probability of A intersecting B, A and B. Which actually you can see is the same formula, but when we're in a mutually exclusive situation, our intersection or the and situation is emptiness. So if we subtract emptiness, that doesn't affect anything. So really the same formula. And something with keywords, some people hear this in elementary school. Some people don't hear it till much later in life. Some people may never hear it. I heard it back in elementary school, but then I remember a couple days in my undergrad math studies, there were people in 300-400 level classes that had never heard this. But add ors and multiply ands. If you have not heard that, that's consistent across the board in mathematics. There's a slight catch for that with probabilities. We'll get to here in just a second, but the ors, add the ors do hold. There's a catch on that whenever the probabilities affect each other that we will get to here in just a second, but that's something consistent. Add the ors, multiply the ands, which I don't think anybody in here had me for the SDEV 120 class. I always try to point out our order of operations for logical operators follows our regular ones, because add the ors, multiply the ands, and when we do a logical operation, and gets done before or. Just like in our normal base 10 mathematics that we've learned since elementary school, the order of operations has this multiply prior to any adding. So the order of operations on logical operators are the same order. It's just hard to see. It's hard to see if you just rushing through it in like a class lecture and don't take time to pause and think it through. So this situation I want to kind of do an example of, which I'm going to write first example here. So hopefully a big hint that, remember, once we have 10 points worth of questions there, I'll write up the math quiz, and I will be looking at these recordings as I write that quiz. So our first explicit example is probably a good indication of the type of thing that is going to be on that quiz. So let's say we have 10 people, and we can categorize them as follows. So we have some males and female, some men and some women. And we're only concerned with eye color here. So a simple case. So we either have brown eyes or blue eyes. And yeah, that's our entire sample. We're not gonna worry about people with other eyes. So it's only 10 people. So there's a good chance we might only find those two colors. So we can make a little chart here. And then throw in a total row and a total column. So what up here? So we have 3 males or 3 men with brown eyes and 2 women with brown eyes, giving a total of 5 people with brown eyes. Might only have one of our 10 people was a man with blue eyes, and 4 of the women we counted had blue eyes. We can give this a total of 5 people with blue eyes. So 3 plus 1, it's like we counted 4 men and 6 women in our sample, and you can see both our total row and total column add up to the same number. So we might have a situation like this, and we can ask some questions about it, some and or questions. So we'll get to the multiply ands here very shortly. But first off, those might affect each other. Those values might not be completely separated as far as the color of eyes of people we ask that question to, or the ratio of people with certain color eyes for each gender isn't necessarily a completely independent event. But we can ask some questions about this chart here. So things like the chance a random person is brown-eyed man or male. I put male in the chart, so I'll put that in the question. So that's back to our original definition. Just a simple question. Chances is a man with brown eyes, and well, it's chosen at random, so that means the total number of things that could happen are the 10 people we looked at. And then our top number is just going to be the number of males with brown eyes, so we can pull that right off the chart. We can combine some of these things. What about just the chance of brown-eyed person? Which, to add the keywords in there, that would be male or female. So first off, we just looked at 2 formulas for this. Are those mutually exclusive? Is there any overlap between the males and females? Without getting into the definitions, just the categories, not worrying about which category people choose for themselves. Because even once people choose a category, it's one or the other category, right? So there's not any overlap. Those are mutually exclusive events as far as which column of the chart they went into. So that means that we'll add them up. The probability of a brown-eyed male or the probability of a brown-eyed female. And those we can pull right off here. So, well, we already have the first one. That's a 3 out of a 10 chance. Or brown eyes on a woman is a 2 out of a 10 chance. And ever since elementary school, you've probably had math teachers tell you to reduce fractions and drill that into your head over and over again. And this is an example of why we shouldn't be taught that, because if you instinctually reduce that fraction when you saw it, you have to undo that in order to actually do the math on it. Same thing if we had any overlap and needed to subtract it. All right, we just add those up. And there's a 5 out of a 10 chance. 5 in 10 chance of those similar things. So there's that. That's the sort of question, one of the questions to expect on the quiz for this section. There'll be a chart or maybe just a list of the data so that you'll need to put that chart together yourself. But it'll be a really quick, easy one to jot down. It might not be mutually exclusive, so make sure you think about the situation. And then what's another question could be asked here? The chance or probability, I put chance last 2 times. Odds, haven't used that word yet. Odds of not blue-eyed female. So going back to our chart, we can pull all those numbers right off there. Again, everything, all our stuff adds up. So not blue-eyed, that would be brown-eyed male or brown-eyed female or blue-eyed male. So we could add all those up. Or alternatively, we could use that rule that was written up there earlier, where all of our probabilities add up to 1. So if we need the complement of something, a quick way to find it is to subtract the probability that's easy to find. So we want not blue-eyed female, so if we take 1 minus the probability of a blue-eyed female, we'll get the same result as if we were to have added up all those different sections. Obviously, sometimes our situations, such as doing this, setting up these formulas in a game for certain events to happen, tables like this would get rather large based off the previous events that happened, right? A role-playing game, you might need a column for regular clothes, leather armor, steel armor, magic armor, and rows of a basic stick, a dagger, a sword, a bow and arrow, an axe. And we'll have a rather large chart like that we want to set up the different situations for how interactions with NPCs or mobs might occur, to tie this back into the subject we're actually studying and hopefully make it a little more interesting. You probably saw something like this in elementary school, but we'll see those in explicit examples soon. As time allows, it's still going to be a very simplified one because obviously we're very restricted on time here. So if we take 1 minus that, probability of blue-eyed female is a lot easier to find because that's just one of our charts. And that's an and situation, right? Blue eyes and female intersect at that point. So that's a 4 out of 10 chance. So 1 minus 4/10 gives us 6/10, or 60%, which is what we would have gotten if we added up 30% plus 20% plus another 10%. It's just shorter this way. And as the data represented in this table here gets more complicated, like that example I just showed, where we might have columns of the armor our characters wearing intersecting with rows of the weapon our characters carrying, or other things, hit points, stamina points, all that stuff, to define how things are going to interact in our game. However we define that interaction, that's going to be a much more complicated table than this chart. So it gives us a much easier way to find that and jump right to a formula. How much more do I have? I have about a page and a half left on the notes. I was hoping that would be done about 7:02. Do you have anything else on this? I'll do that in the break. So yeah, this seems like a good stopping point. There's like a 1-sentence thing and then another example. So I was trying to decide if I should do that 1-sentence thing, which y'all have probably noticed I ramble on a little sometimes. So that would probably turn into more than 1 sentence that I have written in my notes. So this might be a good pause point because that'll relate to the next thing on there. And yeah, really the next 1.5. We're about here on the notes. And it goes down to about here on the next page. So less than a page left, but probably longer than would be the reasonable break time, right? So the big thing here, I'm kind of going on the assumption everybody's seen some probability before. It usually shows up, at least the basics of it, in elementary school, like this calculation we just did, the sort of thing that's going to be on the quiz. The big thing I wanted to cover was to make sure and use some of the formal math notation, because our textbook had some nice sentence explanations of this. But if you get confused at points and go to look things up, you're going to see the formal math notation. So I want to make sure everybody can read that. That's the focal point here, and I'm kind of assuming that you've seen these parts before. Well, the notation and a preview of what sort of questions are going to be on our math quiz when we get to that. But this seems like a good pause point before we finish the last page or so of notes. And then we'll look at version control so that y'all are able to share your Unity projects in that discussion board we just set up. But does 10 minutes sound good to everybody? Or anybody? So it's 7:04. So we'll get back to it at 7:14. I'm gonna go grab some coffee because I'm getting a little thirsty after talking for an hour straight. I'll see y'all in just a moment.